and hopefully more than one person in Twitch will show up. Hopefully I get some play in Zoom. Alright, well, I'm going to start here with the final exam. So, perhaps next week there will be more interest. Or maybe people just don't like 10 o'clock in the morning. Alright, 7 and... Alright. So, I'm going to do what I've done for all my exam reviews, and I'm going to talk about the equations available first, and then we'll find out, and then we will go through the exam itself, and then we'll see if we have more people, and if I should do something else, or maybe we'll see. We'll see. I am prepared to go for a very long time, with breaks, of course, but we'll see if that happens. Okay, so for the first set of chapters here, we have this lovely set of equations here. The first row here, these are called the... I should probably be writing in black. These are the kinematic equations here. And basically, what they do is they describe motion. For us, they are all for constant acceleration. So here we have our velocity given initial velocity and acceleration in time. We have a position. So I call this the velocity equation because it tells us what velocity is. We have the position equation. This tells us what our position is given an initial position, initial velocity, and an acceleration. This one I call the energy equation because it comes from energy conservation. We have the let's see here. This would be 1/2. Ooh, that's terrible. Half. 1/2 mv squared is equal to 1/2 mv naught squared plus initial position in initial position in height, which would be a g, or some other way of getting constant acceleration. All the m's cancel out, multiply both sides by 2, and you have v squared is equal to v naught squared plus 2ad. So I call that the energy equation. And then this one, I believe it comes from something, I think you can derive it from momentum, I think. I'm not entirely sure about that. But it's basically an average velocity. So we have v initial plus v final over 2. So that's an average times t. Basically it looks like, basically it's the position formula where the acceleration has been changed out in such a way that it turns into an average, velocity. So here we have our gravity. This is our force due. This is our weight, also known as force due to gravity. We have sums of forces in a direction is equal to mass times the acceleration in that direction. This is the force of friction, kinetic friction. So if you have a thing that is moving and mu is non-zero, then your force of friction is equal to coefficient of friction times force normal. This one is the static friction, which maxes out at the coefficient of friction times force normal, but is exactly equal to the force required to keep the object from moving when a different force is applied to it. And then this is the spring force here. Normal is not provided, but normal forces, tension forces, and friction static forces. These are what I like to call conditional forces. Conditional forces. Basically, these forces take on the value such that a condition is satisfied. So a normal force is the force required to keep an object from falling through a surface. Static friction is the friction required to keep an object from moving, and tension is the force required to make one end or the other end of a string move when the string itself moves, or basically hold the whole thing stationary. And we have been kindly provided the quadratic equation. That covers chapters 1 through 5, which is mostly constant acceleration and the force equations. Personally, if I were writing this book, I would then skip down to chapter 9, where we return to rotational motion, and we rehash everything again. So all our forces, for every x there's a theta, for every v there's an omega, for every a there's an alpha, for every m there's an I, for every force there is a torque. I think that's most of these. Yeah, for every mass there's a moment of inertia, for every force there's a torque. I think that's about it. So it's basically the same equations rehashed again, except instead of going in a straight line measured in meters, there is now a rotation measured in radians, revolutions, or degrees. I prefer radians because that is the natural unit of angle. 1 radian is the angle required such that this r here is the r around a circle. So there's our theta there. So then theta is equal to, here we are. So the theta is equal to the distance around the circle, s, divided by the radius of the circle. So this is in meters and this is in meters, which means that a radian has unit 1. And that just makes everything a whole lot easier to deal with. It doesn't make a whole lot of intuitive sense, mostly because pi is half a circle, which is why there's a lot of people who like tau, which is a whole circle. And pi is irrational, which makes life all kinds of fun. Oops. Put the degree back there. In DEG. So that covers that covers this bunch here. Covers that one there. So then there is, of course, there is a conversion. So there's a conversion from angle to distance around a circle, or if the circle is not slipping and rolling along a surface, then distance that that circle travels. Same thing here, where we have a conversion from angular velocity to actual velocity. Here we have angular acceleration to tangential acceleration. And then, so if you're going around a circle this way, you can have your velocity going around the circle be changing, and so then you end up with an a tan here equal to alpha alpha r, or r alpha. But because you're going in a circle, your direction is changing, so you need a centripetal force going inwards, and so this is v square on r, or r omega square. And you can use this v equal r omega to prove to yourself that these are in fact equivalent to each other. So this is our a rad inwards. I think that's all of that. So if we have so then we have I is our moment of inertia, which is we have been given I for various point particles. So if you have a thing going around a circle, lovely circle there, with mass m, that's terrible m, try again, with m and r, then its moment of inertia is mr squared. If you have a rod going around a center point or a disk, that's a lovely disk. Try this again. There we go. Rotating with omega, then it'll have an I based on this. That I is going to be provided to you either as an I is equal to a certain value, or an equation will be provided to you such that, like, if you have disk, it'll say I is equal, that's a little bit I is equal to 1/2 m r squared for a disk that's rotating about center, and other such possible equations. Then I would, if I were writing this book, I would go into let's see here. Well, let's see here. This year, yeah, I think I would then go for, when I was doing the rotational motion here, I would also then include the orbital stuff here. So we have a force of gravity. This force of gravity here is for satellites and other such lovely objects. Just out of curiosity, anyone else in here? Nope, just me all by myself. Here. So there's a force of gravity which is mg. This is for over small distances, whereas this force of gravity is for over large distances, which would be for satellites and such. But we can, from this equation here, that these actually have to be equal to each other, we can derive this g by going, oh yes, this is m1, this cancels there, that cancels there. Therefore, g, little g here, this 9.8, must be Newton's constant times the mass of the Earth divided by its radius squared. And that should produce this answer here. This is the period of a satellite going around some, well, it's written for Earth, but it could be just about anything. And then we would get into energy. Physicists really love our conserved quantities, and energy is one of those. And so all of these equations here is about tracking down where the energy comes from and where does it go, and in what way does it go that way. So we have work done by a force in the direction of the travel is equal to, so yeah, work is equal to force times distance traveled by its parallel amount. So I prefer to write it as FD cosine theta. So it's basically saying how much force was done parallel to the travel is equal to our work. This is our work total, which is the change in kinetic energy. And our kinetic energy is 1/2 mv squared, which I used up here to rederive this equation, justifying why I call it the energy equation. Then we have two potentials provided to us. We have the gravitational potential over short distances, and then we have elastic potential. If you really wanted a UG over large distances, then you would have to take the negative derivative of this equation here, and we would find that it is minus GM2 on R. And when you get into next semester, you'll see that again, except instead of G, it is K, which is for, nope, don't do that, which is Coulomb's potential. So here we have our, basically it's energy conservation, and this work other is looking for other things like friction, or some other work other that has been provided to you. Usually, quite often, will be friction. And so you need to make use of this F dot D here, F D cosine theta, to work out what that work other is. Here we have power. Power being work over time is the work done over a certain amount of time. And so you can ask the questions about the power total or the power of a certain force. And then we have this one. This is power. This is another way of writing power. Basically, it's taking advantage of F times. Is basically looking at this one here. F times our distance traveled. And goes, well, we're doing a change in time, so this is actually force times our velocity, and that's most of the power. Technically there's another term here, which you need to be, which I should probably not be bothering with, but there's that other one. But in this class we won't bother with that because it's calculus. And then we have momentum. Momentum is another conserved quantity. Momentum being mass times velocity. It's often a conserved quantity. When it's not conserved, the change in momentum is equal to the impulse. They use J in this class for that, but is equal to force times the force applied times the time that the force was applied for. So if the force was applied for a very short period of time, then this can be small, unless the force is large, in which case, never mind, it cancels each other out. There are ways to basically say that the impulse from one object is equal and opposite to the impulse of another object. Which is basically the same, which is another way of writing down Newton's second law. For every action, there's an equal and opposite reaction. So one object will have its impulse, and then the other object will have negative impulse. This is basically writing down the same thing as this here, only this is for several particles. If you wanted to do an average of some kind or another. So one of the questions I will get from time to time is, how do you know when energy is conserved or when momentum is conserved? As far as this class is concerned, so energy conserved, E conserved, when you look at an event, you can tell which way it is going. So if you have one object comes in, another object comes in, and then they stick together as one object, you can tell that. So in this particular case, you can tell energy is not conserved because you can tell whether this is going forward or backwards. Usually off of context clues, but it's like a bullet comes in and it gets embedded in the object. It's like, well, yeah, there's only one direction that can go. It's going this way. Or another way you might see it is as an explosion, where it's like the object is going back this way and then it explodes. So, well, of course, there's only one way that can go. You must detonate some amount of explosive in order to make that happen. They just don't fall apart. So then you can tell that energy is not conserved in that particular case. This here, another. Whereas, say, with a ball going up in the air and coming down, is he going this way or is he going that way? No, you can't tell. Because it's going in parallel, so you can't tell whether the film is going forwards or backwards. You have to kind of guess at that, and so in this case, energy is conserved. For momentum is conserved when when there's no forces applied from the outside. So in that case, then the momentum must be 0. think that's about it for those chapters there. All right, scrolling on down. Finishing off our little chapter here on rotational motion, we have torque. Torque being, generally speaking, so we have torque. That's interesting. One moment. There's if you're gonna put the parallel in here, you might as well put the perpendicular here. Come on, man. Really? Are we getting lazy or what? So torque is equal to force perpendicular to the lever arm. I like R instead of L for that particular case, which means that this is equal to FR sine theta instead of the cosine theta up here. Which of course means that torque is in order to differentiate torque from work, this is reported in Newton meters and this is reported in joules, even though that those contain the exact same unit. But torque is also equal to I alpha, so the sum of torques is equal to, just as there's an F, just as F equals MA, there's a tau is equal to I alpha. So M becomes I, A becomes alpha, therefore force must become torque. And these of course are equal to each other. So then you end up with a sum of, right. So the sum of torques, this being this bit here, is equal to your total I alpha. Work is equal to the torque times the distance times the rotational distance that is applied. Power, same thing as above. This is our angular momentum, and then this is the equivalent of, I believe it's your torque. Yeah, this is the equivalent of impulse of this one here. So so here's our delta. So F delta T being our change in momentum. Here's our change in angular momentum equal to, move this over here. Change of angular momentum is equal to torque times time that is applied over. And this is the angular momentum for a single particle going around in a circle. I believe that's about it there. Let's see here. Anybody in my Zoom? Nobody in my Zoom to answer the question if anybody has questions. And let's see if there's anybody in my Twitch chat to have questions there. Come here. Twitch chat. There is somebody in here. Yay. Another TV viewer. Okay. Interesting. No. So I got one watcher. We'll see if. So I might be just talking into the void for 2 hours. Alright, let's see. Okay. Continuing on. So then we have if an object is not moving, then the forces applied to it must be 0. That's what these first two are. Forces in x is equal to 0, force in y is equal to 0, and if it's not rotating, then torque must also be equal to 0. And then from there, I believe that's about it. When you do an equilibrium problem where you have possibility of rotating things, I recommend you put your pivot where one of the forces is applied, therefore that force applies no torque. And then you can simplify your problem in that way. Alright. These here, this is Young's modulus, bulk modulus, and shear modulus. And in this class, those ideas tend to get the short end of the deal, and so I shall be skipping over them. Alright, okay. Oscillations. Let me write on the right surface, there we go. So we have force is equal to, so here's our spring force again, is back. And then from M A is equal to minus kx, we can find this here. If you were to then solve this differential equation, you would find that, no, you don't need to solve this. This is the basic definition of angular frequency and how it relates to simple frequency of an oscillation. This omega here is different from this omega here. This is angular velocity, whereas this here is angular frequency. They are not the same, even if they are in the same units. They can be the same for uniform circular motion. And that is the only case in which they are the same. But if you have a pendulum, if you have a pendulum, it's possible for it. I have seen this problem before, but it usually does not get asked because of the chances of omegas being confused. Where you can say, what is the angular frequency of a pendulum? Not the angular frequency. What is the angular velocity of a pendulum as it swings through a certain point? Usually the bottom. Yeah, it has to be through the bottom. And so you can go, right, on 1/2 I omega square is equal to mgh, and then you move things around and you figure out what the omega is, which is not the same as this omega, because if you were dealing with a pendulum, you would end up with, where'd it go? You would end up with this here, where you find that omega is equal to square root of g on L. So this would be the angular frequency of a pendulum, but this could be the angular velocity of that pendulum as it goes through the bottom of a swing. And these two omegas would not be the same. And then that has caused problems before, and so usually I have seen cause problems before, and so quite often it will not be asked on any given exam. Frequency is one of the period. Here we have our kinetic energy and spring force, spring energy again. And then this is the solution to this differential equation, and then this is the first derivative of that solution. And given this equation, you can find that the a of x from this bit here, being negative omega times this answer here, negative omega squared. You can see the k on m here and the square root of k on m here, so this is minus omega. So this is the same as minus omega squared x. Lovely. There we are. Try that again. So here's our frequency for our frequency and angular frequency for a mass on a spring. This is the period for mass on a spring. These two are for the pendulum, period of pendulum, and the frequency for pendulum. And then we get into standing waves, into wave velocities and such. So then we have velocity of any wave, and this is velocity of a wave on a string with our force tension and the linear density, and then this is the equation for the wave as it travels along a string, or any wave in particular, where if say so if it's a wave on a string, then y is the displacement from center, but it could be a sound wave where y is equal to the air pressure of that wave, or it would actually be the change of air pressure from a standard air pressure. But if we wanted to say add air pressure, let's see here, add +1 atmosphere, then you would have the pressure of a sound wave, pressure of air as sound travels through it. We have, these are the frequencies for a standing wave. This one here is for, let's see, make sure it's right. This one's for, say, a pipe that is open on both ends, or a pipe that's closed on both ends, or a string where both ends are pinned down, and so you end up with a string that looks like that. Or which I would draw the sound wave in here, would look like that, or the sound wave in this one would have to be antinodes on both ends. Whereas this one here, you have a string which is pinned on one end and open on the other. So basically you take a string, you could take it on the one here, you could take a string and spin around on top, and then the bottom end would have to be swinging way out here. Or you would have a pipe which is closed on one end, so you have the node on one end and the antinode on the other end. This would be the case for, say, would also be the case for if you had a bay where you had the ocean out here and waves would come in and go out, and waves would come in and go out, and then you could look at the standing waves in that particular bay, and then if the frequency, say, I think like the Bay of Fundy is where this is a case where the frequency of the tide is the same as the as one of the standing waves of the bay itself, and so you actually get unusually strong tides going through there. Here we have the intensity of sound given the initial power of the sound in question, and then this is the decibel sound of that particular thing. So we have this would be a common log. I would like to have 10 in there. This is the common log times 10 dB. So we have the decibel of a sound. Basically, it's comparing the sound that you hear to some threshold. It could also be comparing two sounds, like this sound is this many more dB than another sound, and so then this sound would go here, and that other sound would go over on top of it. This is the beat frequency of two sounds. So if you had, let's say, a 440 and a 441 hertz, then you would hear them pulse in and out. With a, you would hear a you'd probably hear something like a 440 and a half hertz sound pulse with the frequency of 1 hertz, and that pulsing would be the beat frequency. Here we have Doppler shift, frequency of a source, the frequency that a listener hears, given the listener, the velocity of the listener, and velocity of the source. I prefer to put pluses and minuses here, and then you have to pick a plus and minus such that the expected outcome happens. So if the listener is approaching the source, then you expect a higher sound, and so you pick the plus, whereas if the listener is leaving the source, then you put a minus. Temperature, and then we get into thermodynamics. We have the temperature conversions from Celsius to Kelvin, Fahrenheit to Celsius, Celsius to Fahrenheit. And then we have thermal expansions for a line, for a linear thing, like rods, train tracks. I think that's probably most of what you're going to come across. Thermal expansion for volume, where you have a liquid or a fluid of, or some volume of mercury in a thermometer. I think that's most of what you're going to come across there. I still don't know what this is. This looks like a pressure of some sort, but I'm not sure what it's equal to. So that's probably nothing we're going to be concerned about. And then we get into moving heat around. So this is known as calorimetry. When you have a calorimetry problem, you're going to be looking at sum of Q is equal to 0, And so you look at how much you're going to heat something up by or cool it off by, and you're going to add in there any melting or vaporizing or condensing or freezing. Freezing terms would come up in here, and then you put them all on one side, and you set them equal to, add them all up, and then you set it equal to 0, and then you can move things around and solve for the correct answer, hopefully. Unlike last time I did that problem where I tried it 3 different times, I had to do it 3 times to get the correct answer. That was most unfortunate. And then we have heat flow. So we have conduction going from where we conduct heat from the hot side to the cold side over some distance across some area, and that material has a thermal conductivity. K will always be given because we don't need you to be measuring things. It is possible that you could, in fact, instead be given the heat flow and the hot and the cold and the length and the area, and be told to say what is K. It's also possible for, say, where you have 3, most likely you'll have a T hot, T cold, and T in the middle of the interface here. And you're told, and in some way or another, you're let's see here. Right, and the heat from here has to be equal, the heat flowing through this object has to be equal to the heat flowing through that object. And then from that you can solve for the T in the middle. Whereas you basically have a T hot, and then where you have 2 copies of this, and one TC is the T in the middle, and the other, and for the other side you have the TH is the T in the middle, but they're equal to each other. And then this is radiation. This is for an object radiating heat into the void. But it is possible where you say have a coffee pot with say 90 Celsius, and then outside where it's 20 Celsius, and then you have to take the difference where you can say it is radiating out into the void a certain amount of heat, and then but it has to be receiving a certain amount of heat back from the environment, and so you basically end up with an H is equal to A E sigma T going out minus the T coming in, kind of a thing. And then from this you can figure out how much is, so then you have the heat energy being radiating out and heat energy being radiated in. You end up with a total heat being radiated away. Let's see here. We have the ideal gas law, PV equal nRT, and then there should be a conversion around here somewhere. Here it is, where you turn it into let's see here. I'll bet there should be a conversion ratio around here somewhere involving Avogadro's number. Yeah. Now, well, PV equal nRT, where you have the mole of the molecules, mole numbers, or it could be in KT, where you have the actual number of particles here. Let's see here. Rho equal PM RT. I think this is another conversion of the, yeah. This is like a density. So density of air, or whatever it is you have, equal PM. I'm not sure what M is, but it has something to do with this M here. Oh, it's molar mass. It's molar mass. So this is the density of the air is equal to pressure, molar mass, divided by RT. So it's basically another rehash of the ideal gas law, except it's for a specific amount of the stuff rather than for a total amount of the stuff. So it's a density and a molar mass, or a specific mass of the gas in question. Constants. floating around. This is the average kinetic translational energy of the gas. This is basically one. It's yeah. Here we are. So here's the 1/2 mv square is equal to 3/2 kt square, and using the same conversion going from nr to nk, you can basically do that. Convert this 3/2 kt to 3/2 nrt. There's a conversion between those two. And then you can solve this for v, and you get this lovely stuff over here. The rest of this is engines, which I do not believe actually landed on, you actually managed to get through. So I think I will go ahead and avoid that for now. So now I've gone through and explained I think most of the equations that are of interest in this class. Whew. This here. Yes. I have a sneaky suspicion that I may go for long periods of time. So I will go ahead and insert a break here. We're going to take a 5-minute break here.